Hello and welcome to today's IWCS webinar. My name is Connie and I'll be the WebEx producer for today's event.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box in the bottom right of your screen to post a question anonymously. And we encourage you to post during the presentation if you wish. Contact the presenter or IWCS after the presentation. You will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Riley Freeland, Development Associate, Corning Research and Development Corporation in New York, USA, who will be presenting his paper on strain sensing of an in-road FTTH field trial and implications for network reliability. Riley Freeland is a Development Associate at Corning Research and Development Corporation in Corning, New York. He joined Corning in 2001 and has served as a measurements engineer, analyst, and solution designer. He received a BS in engineering physics from Cornell University in 1995 and a PhD in atomic and molecular optical physics from the University of Texas at Austin in 2001. Riley, we welcome you to present at today's IWCS webinar series events.
Thank you very much, Ed. Thanks, Connie. I appreciate the chance to talk today, and thank you very much for that introduction. So the motivation for this work is the value that fiber to the home brings to the end user. This is some quotes from multiple studies that demonstrate the value that fiber to the home gives. The box on the left shows the discounts that some homes need to consider similar non-fiber broadband homes. So for example, a home without fiber broadband would need a 3% discount relative to a home with broadband. Another study found that a gigabit connection can increase the value of a transaction price by as much as 7%. And so these are just some of the motivators that drive deployment of fiber to the home and the value to end customers. One of the biggest drivers for cost of deploying fiber to the home is the installation cost. And in fact, it can be as much as 50% of the total. Two main methods are used to install fiber in an area. Aerial, you see the bucket truck on the bottom, or buried, where cables are trenched in the ground directly. Aerial is usually faster and less expensive than buried, but it requires the use of existing poles or installation of new poles. But some communities don't allow aerial deployments, and that leaves buried as the only option. And so some service providers have done all they can with the aerial deployments, and they've actually deferred the buried deployments. And so the technology of buried deployments involves things like directional boring. And the directional boring has come down in cost recently, but it can still be unaffordable in many areas. And so in this paper, we've described an alternate strategy for a buried deployment, which has the opportunity to reduce installation costs. In this new method, cables are placed in a shallow slot cut into the road. So the slot doesn't go all the way through the asphalt, but instead it's only about 10 centimeters deep and about 2 centimeters wide, so about 4 inches by 1 inch. Other types of roadway installations that people have done in the past can be as much as a meter below the surface of the road, and it can be much wider. So this small slot is much faster to cut. The photo on the left shows the slot cutting and vacuuming machine. After placing the cables in the slot, they're filled with a rugged compound which rebonds the asphalt. Those middle two photos show the cables placed in the road and then then filler applied after that. The final step is to cover with a sandy top coat. The rightmost picture shows the final appearance of that slot 1 year afterwards. And so one advantage of this method is that standard tools can be used for cutting these slots in the road. Another advantage is that directional boring isn't necessary. And so the majority of the work takes place on public right-of-way, and it leaves customer property undisturbed. Another advantage is that standard cables can be used in the network. So you don't need special metal-clad cables or other reinforced cables. So standard aerial or buried cables can be used. And so innovative methods such as these can be used to drive down the cost of fiber-to-the-home deployments. But because they are new, there might be some unexplored risks that service providers might have some caution about when trying a new technique like this. So one of the key risks is the effect of asphalt movement on the cables and the resulting reliability implications. So cables are embedded in the roadway, but the road isn't really a static structure. It moves and flexes and changes over time. And so some of the defects are shown here in these photos. The photo on the left shows a crack going across the slot in the road. And this is before the top coat was put on, and so that filler compound has that glossy kind of look to it. And so the cable ran right across that crack. The photo on the right shows a section of the asphalt that had been eroded over time. There's been some subsurface and surface damage to the road, and you see some cracking and fracturing, and then the slot going across that eroded section. And so it's precisely sections like these that are the most interest for testing and analyzing to see how defects like this can affect the cable reliability and how the cables respond to changes in the asphalt in these sections. So to assess the risk, we used some distributed sensing cables and deployed those in the roadway along with the network cables. The sensor cables were monitored using the Luna optical backscatter reflectometer, the OBR 4600, and that performs a distributed fiber strain measurement. The OBR uses Rayleigh backscatter as the sensing mechanism, and because of that, it can measure changes in strain or changes in temperature, and we'll analyze those later on. Also, the spatial resolution of this measurement is about 7 to 10 centimeters. And that means we can see cracks spaced just a few centimeters apart down the road. In this test, we also used a couple of different kinds of cables. The connections from the distribution cable to customers were made with this SST drop cable in the middle. The primary cable was the rectangular profile ribbon cable, or the RPF cable, shown at the top. Both of these carry live network traffic, and both of these also have a small amount of excess fiber length. And that small amount of EFL allows the fiber to bend and flex inside the cable, and it buffers the fiber from the environmental stress. And that way, even though the cable can experience strain, the fibers will be strain-free up to a point. The last cable is the distributed sensor cable, or DSC. In this cable, the fiber is directly embedded in the jacket of the cable, and it bonds the fiber essentially to those strength elements. And because of that, the DSC is a very effective strain sensor. There's no EFL, and that means that any environmental stress is translated to strain on the cable and strain on the fiber. And we'll use this to interrogate how the road and asphalt is changing over time. This photo shows an example of a slot a core sample taken out of roadway. You see the asphalt with the rocks embedded, and in the middle is a slot. The top coat is there at the top of the slot. The filler is below that. And in this particular piece, there was a duct with a toning wire and one of the RPX distribution cables. In places where we put the DSC cables in the slot as well, they would have been at the bottom of the slot with the network cables, the RPX, and the drop cables on top. For testing, let's first look at neighborhood A. In this neighborhood, 2 test sites were chosen. Here you see a map of the neighborhood along with the path of the distribution cables. The distribution cables were split into sections inside a duct along the main road, and then branched off from that where the distribution cables were trenched into the road itself as the single lines. The sensor locations are shown as A1 and A2. A1 was at a cul-de-sac, and A2 was along the distribution cable itself. These cables were installed in August of 2014, and during the summer, the average daily temperature was about 23 degrees C, and in winter, -9 degrees C. So the average summer to winter temperature fluctuated by 30 degrees. So looking closer at that site A1, the cul-de-sac, the test set, or the start of the cable, was at position A. It ran from A through the curb at D, across the road to C, then around the cul-de-sac through the slot to D, and then from D to E, the cable went through a duct. And the photo on the right shows the view of that cul-de-sac. You see the test set located at point A, and then the cable ran from A across the road to C, around the cul-de-sac to D, and then back through that duct from D to E. This plot shows the strain along the length of the cable of actually 2 sensor cables that were installed in that same slot. And this is in March of 2015, so some months after the initial installation. The figure shows the change in strain on the vertical axis and length along the cable on the horizontal axis. The markers A, B, C, D, and E are shown at their proper positions on the plot. Some other things to notice are that the crack locations in the asphalt are shown as the gray markers across the top of the plot. So some things to notice. First of all, we can see that the high strain events are generally correlated with those known asphalt crack locations. For example, there at the 60-meter mark, the strain is high, and there were 2 cracks very close to each other. And also there, between 20 and 30 meters, there were several cracks located close to each other, and the strain is also very high. Second thing we can note is that the strain in the 2 cables are very similar to each other. Cable A is black, the black data trace, and cable B is the blue data trace. And these overlap almost exactly. The last thing to note is that the strain in the duct in that region between D and E is much less variable than the strain in the roadway. And so from these, we can conclude that this distributed sensor cable really measures strain from the asphalt movement and not strain inherent in any particular piece of cable by itself. So the sensor cable couples the strain from the asphalt through that filling compound into the cable, the strength elements, and the fiber itself. The dashed gray line in this plot is the average strain from the 10 meter to 70 meter markers. And that average strain is equal to what you see in the duct portion. And so in fact, that difference in that average strain and that duct portion is really just the temperature offset of March as opposed to the initial measurement in August. This next plot shows the strain in one of those same sensor cables over 2 years of monitoring. Traces in the bluish colors represent measurements in winter. Traces in the reddish colors represent measurements in the summer. From these measurements, we can see that the variability is highest during the winter. So the peak-to-peak amplitude is highest for the blue curves. The red curves, taken during summer, we see that the strain returns to near baseline levels. The peak-to-peak amplitude is much lower, and the average strain is near zero. From this, we see that the strain is seasonal in nature, and it doesn't increase over time. So this kind of makes sense. Each individual piece of asphalt between two cracks expands and contracts during the summer and winter months, but the asphalt doesn't keep increasing in length over time. There's no overall length from one house to another as time goes on. And so the average strain remains pretty consistent, but the peak-to-peak changes between summer and winter. And so we can move on to sensor site A2. In this case, our test set was at A. The cable ran along the slot to B, turned the corner, went across the road to point C, reversed itself, and then followed the same path to B and then back to A. So in this case, we had one sensor cable in the slot, but it traced its path forwards and backwards. This figure shows the strain in that sensor cable versus length. The overall length from A to C and back was about 200 meters. And you can see that point C, the reversal point, the strain is symmetric about that reversal point. And so whatever cracks and defects and sections of asphalt that are changing over time, this distributed sensor cable picks that up and it mirrors it on each side of that reversal point. And so in fact, the section between 40 and 60 meters, where the strain is pretty quiet, is mirrored with the section around 180 and 190 meters. And so again, this shows us that these distributed sensor cables are very sensitive to their environment. And then lastly, I wanted to describe the deployment at Site B. This was a different location in a different part of the country. In this place, multiple cable types were installed in the same slot. And so here we'll look at the distributed strain sensor cable, the DSC, the drop cable, and the RPX distribution cable. In this location, between points A and B, the drop cable and DSC were installed right next to each other. And then joining in at point C was the RPX distribution cable. So from B to C, all three cables were in the same slot. So this figure shows the DSC, the strain sensor cable, running from A to B. And again, we see that the DSC strain varies seasonally, with winter having the highest peak-to-peak strain changes and summer returning to baseline levels. This next figure is going to overlay the strain from the drop cable on top of the DSC. So now we're looking at the drop cable strain, and the red curve is much smoother than the DSC, and likewise the blue curve is much smoother than the DSC. This SST drop cable is free of strain events. So it's going along the same path from A to B, but you don't see the high peak-to-peak strain changes. Again, this drop cable has excess fiber length, and so as the asphalt expands and contracts, and the cracks in the asphalt expand and contract likewise, the fiber is free to move inside the drop cable, and therefore it's buffered from these environmental effects. And we see a difference between the summer and winter months. And in fact, that 0.025 strain difference should really be interpreted as a temperature difference. So remember, we're using a Luna OBR to measure strain. And the way it measures, it really can't distinguish between strain and temperature variation. It's up to the operator to make that decision. And so the plot shows this difference as a strain difference, but it's better interpreted as a temperature difference. And that temperature difference is about 30 degrees C, which is what we expect at this test site for the average summer and winter daily differences. And in fact, if you take the average strain of the DSC cable, the blue trace in the background with the high peak-to-peak amplitude, it's approximately equal to the average of the drop cable. And then lastly, let's look at the RPF distribution cable in the slot starting at C, continuing to B, and moving onwards. And again, this ribbon cable, we see that this is free of strain events along its length. And that, again, the excess fiber length in this cable buffers the fiber from this environmental strain of the roadway. From this experiment, we can see that these network cables, the RPX and the drop, show very little strain variation. And that these seasonal differences are really more due to temperature differences at measurement time rather than strain differences. These three figures are the same three I had up on the previous slide, just showing them next to each other. We can see that from these figures, the network cables, the RPX and the SST drop, show very little strain variation along the length, and that these network cables manage the local asphalt movement with internal ESL. And we see that these road defects do not induce these local high strain events in the network cables. And we see that the strain in the rectangular ribbon cable and the drop cable remains small. And so with this work, we've looked into a novel in-road FTTH solution, which was trialed in several locations. In this method, cables are placed into shallow slots cut directly into the roadway. One risk of this method is that movement of the road can lead to excess strain on the cables. Using the Luna OBR, we monitored strain on the cables for several years. We found that the strain remained low in the network cables, the RPX and the drop. On the other hand, movement of the road was easily visible using the distributed sensor cables. The movement was seasonal, and it did not tend to increase over time. And so as a result, this sort of installation seems to be reliable. And so that means it's been lab tested and it's been field proven. This slot sort of installation is easy to install and it's scalable. And so thank you very much for the chance to present this work. I appreciate your time and your questions. Thank you very much.
And thank you, Riley, for presenting this very interesting and important topic today. We're going to take as many questions from attendees as time permits, starting with this first one. What is the lifespan expected for the integrity of these slots and cables? Is there a problem of cables opening up from these slots themselves due to road use or weather stress?
Right, so the time of this installation is something that is being looked at. The materials selected for this sort of installation are very important to answering that question. And so going forward, understanding the materials, the compatibility of materials will be key.
Okay, thank you. The next question. Is the filler and top coat of a special design so as to not cause deterioration issues with the jacket or fiber optic cable and not create expansion and contraction stress?
Right, so the material selection is very important, and I do not want to go into details right now of what those materials are, but I can follow up with the questioner later.
Okay, that's great. Thank you. Next, when vehicles transverse directly over the slots in the cable, is there a higher probability of strains?
So one of the cable test sites had a cement truck parked on it at one point, and because the slot is very narrow, the load is really transferred directly into the asphalt, and very little goes into the cable itself. So the short answer is tests were done, and the impact of heavy trucks on the slot was found to be essentially none, not measurable.
Okay, thank you. Next, is there a correlation between strain and attenuation data loss causing transmission rate reductions, especially during like the football playoffs or winter?
Right. So again, these the distributed sensor cable did show high strain events because that's what it was designed to do. The network cables, the RPX and the SST drop, did not show those strain events because the excess fiber length inside the cable allowed the fiber to move freely, and so the fiber did not know there was a crack nearby. And so in that sense, the fiber was in a benign environment, and the attenuation was not changed. And so as a result, the network cables did what they were designed to do and mitigated this environmental strain. And the sensor cables, on the other hand, did what they were designed to do and showed these potential asphalt straining locations. So the short answer is the impact to attenuation should be low.
Okay, thank you. Next, what about resurfacing of roadways in the future?
Right, so the slot was chosen to be a depth sufficient so that the regrind process would take off the top few inches of the asphalt, but the cables were embedded deep enough that in many circumstances, I'm not going to say all, but most circumstances, the regrinding and repaving would leave the cables untouched.
Okay, thank you. Next, in the event of an unlikely failure, is this application easily repaired or would it require a complete redeployment?
Right, so there are repair strategies in place that would require the cable to leave the trench, go to a curb, and have some splices done. But there is a repair strategy that would allow the cable to be fixed and not redeployed entirely.
Okay, thank you. point, I see no further questions. So thank you, Riley, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Riley after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, October 18th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 67 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, September 29th through Wednesday, October 2nd, 2019 at the Charlotte Convention Center in Charlotte, North Carolina, USA. In addition, the third annual UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 17th through Thursday, March 19th, 2020 at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's events.